to me in Japanese and I'll translate them, or I'll get the data and I'll actually help them write them or plan them. So that got me thinking, and the reason that I wanted to talk today about the way that basically doctors and scientists work. The hardest part of medicine, I've been told by medical doctors, is actually doing things. You learn stuff in school, but until you actually get to treat patients, you don't really know what you're doing. So doing is the key. But for us as basic scientists, the hardest part of science is the thinking, right? The doing is actually fairly simple. Complex experiments seem complex, but they're very sequential. But thinking up of the experiment is our challenge. Okay. So this creates what's called a fundamental disconnect between what's clinical and scientific thought. And that's basically that the goal of medicine is an outcome orientation. The patient lives or dies, the patient is healed or not healed. Disease is prevented, cured, or encouraged. Okay. Whereas for us as scientists, the goal is actually knowledge oriented. We don't particularly care about the outcome because a failure outcome in science is still knowledge. We know that when we do A plus B, we don't get C. Well, that's actually knowledge, and that's valuable for the rest of us. Now, doctors are individual. It doesn't matter whether there's a team of doctors or a million doctors. When you go see one, there's one doctor that makes the call. Okay? Even in a team, there'll be a head. There'll be a senior doctor who approves all of the decisions. Whereas in science, nobody fights alone. There's thousands and millions of us, and we all try to work together. And there are entire laboratories of 50, 60, 70 people all working on one problem. So doctors face individual patients, scientists face individual problems. Let's put it that way. Doctors tend to focus on bedside care and what works, while scientists tend to focus on mechanisms, reproducibility. If your doctor could cure COVID by throwing you into a pool full of Pocari sweat, then he would just do it and they wouldn't question it because it would work. But we would want to know why, right? So for clinical physicians, the precision is usually in the treatment. Precise dosages, precise administration times, precise cuts of a precise length. Whereas for scientists, the precision tends to be in descriptions of what are called reagents and effects. The precision is molecular. If you take this reagent and react it with this reagent, you get some product. And we're very specific in yield percentages and other things. Whereas dosages are just independent variables for us to manipulate. Yeah, we gave the rats 100 milligrams per kilogram. It didn't work, so we gave them 300. That didn't work either, so we gave them 700. You can't do that in medicine. You can't just randomly give large doses of medication to people. The other thing is that doctors don't really get to fail because when they fail, somebody dies or gets crippled or gets affected. Okay, human misery is the cost of failure in medicine. But for science, we actually thrive on failure. Failure is actually how we learn. We don't like it, but it's part of how science evolves. And last but not least, clinical medicine tends to operate on past evidence. 100 years ago, somebody found something, so they do it today. Science tends to operate on what are called theories. 100 years ago, somebody came up with a theory because that's the evidence that we had at the time. Today, it's a whole different evidence means a new theory. So we can discard theories as we wish and come up with new ones. So this creates like a Mars and Venus kind of situation where the main questions for communication in the clinical side are who, when, what, and how. Who to treat, who to give it to, when to treat, when to not treat, what to treat with, and how to treat, and or how to give it. And the scientists usually just ask why for everything. They're like 3-year-old kids. If you've ever seen 3-year-old kids, they ask why continuously. Okay, that's us. So the solution to this would have to be something that could bridge the space between the two. And there actually is something called translational research, and that's created with a what's called a bench to bedside methodology. And as you can see from the graphic here, it includes basic science things. It includes innovation and IP and development, but it also includes the clinical medical trials, regulatory approval, and the treatment of human diseases. So this basically takes benchtop findings and it accelerates them into patentable and developable medicines or therapies to use in people. It also repurposes clinical data for analysis. So they can take old clinical data from the 80s with some basic science knowledge, and they can use statistics or bioinformatics to extrapolate new hypotheses to test in the laboratory. So we could take an existing antibiotic, for example, that's no longer useful, like penicillin, because everything is resistant to it from overuse. Well, we may be able to take derivatives of penicillin and test them. So we take past data on penicillin modifications and other clinical issues, and we roll that all into a development pipeline for new clinical trials for a penicillin derivative. Okay. And our translational research model is based almost wholly on animal disease. Okay. So we take animal disease models and we use them to substitute for humans. I am a biomedical scientist. I have a PhD in biomedical science with a focus in cardiovascular immunology. So I did a lot of rat surgery. So when I see animal disease, I have this PTSD of having to cut open the necks of hundreds and hundreds of rats. Okay. So the translational communication bridge that we create takes the effect based, remember the outcome or effect based methodology of medicine and the mechanistic or discovery based methodology of science and puts it together where mechanisms are done in the basic and preclinical research and clinical research. The effect is done in the implementation, the public health, and the patient involvement. So we have basically a merging of these two things. Now, this is not new. Almost every PhD program in the United States has a biomedical wing. It's the most popular. We also make the least amount of money as PhDs, so shout out to biomedical science. But commercially, it is also important because, for example, the foods that we eat, agriculture. Now, agriculture is not really a health science. We have an agriculture department on campus, and they focus mostly on crop yields and disease resistance for plants. And plant genes are not usually conserved in people. So that doesn't directly benefit human health. However, the food we eat directly affects human health. And there is a program at the University of Scuba that has actually combined both of those things. I referred to it at the beginning. You may have heard of it. So, uh, there are programs, this is one example, but all over the world, there are programs that are linking diet and exercise and other factors to human disease intervention. And we see these results, these translational results, in things like nutraceuticals, vitamins and supplements. Japan is huge for this. I'm sure Taiwan is too. But you take traditional Chinese medicine or traditional Japanese kampo, which is essentially herbal medicine, and people will test that in scientific settings. So there's a translational bridge from traditional Chinese medicine to nutraceuticals. See? And then we also have medical foods, and you can get prescribed medical foods. For example, probiotics for irritable bowel syndrome, or if you get a colonoscopy, and I hope all of you are too young to have to get one, but when you're in your 40s, they always want to give you one. But they'll give you special foods that are little packets, and they look like real food, they taste like real food, but they help to prepare your digestive system for the procedure so that it goes more smoothly. These are prescribed medical foods. and these were tested in the translational pipeline. Okay. So this creates what's called the new translational paradigm, where the function of research, basic research, is defined. The function of medicine is to apply. So whatever basic science finds and develops, functional medicine applies on the patients. But the function of translational research, and what I'm going to talk about today, is to find and tell so that medicine can more effectively apply. So rather than saying we need an MD, PhD who is both a doctor and a scientist to bridge the communication gap, you can do it with translational research. So you can get a PhD in this, or you can get a master's degree in this. You can study this field and you can study this methodology, and you can go work in a hospital. And the doctors will tell you one thing and you can write it up in a paper. Okay. So how do we do this? Well, basically, I'm going to break it down into three things, which is molecular precision and accuracy under the find heading, critical thinking, which is again under the find heading, and then the manuscript dissemination. We're going to talk about paper writing because that's basically my job. That's what I know the most about. So that's under the tell heading. Okay. So first we're going to talk about molecular precision and accuracy, which is under the find heading. And molecular precision is important because names have to be consistent. Now, how many genes are in the human body? Thousands, right? At least 3 or 4 or 5,000, something like that. And a lot of those genes have multiple names. It's almost like kanji or the Chinese characters, where, like in Japan, one kanji will have maybe 3 or 4 different ways to say it, and you have to remember all of them. Gene names are very similar. But those gene names have to be consistent so we can tie them to mechanistic consequences, especially health outcomes. Okay, this gene does this thing causes this disease. That's the foundation of translational research. And these associations must be consistent. They have to be reproducible. So, as a graduate student, the first time you get a good Western blot, yeah, do it 7 more times and get the same result. So that's what my professor used to tell me. Don't come to me with a Western blot until you've reproduced it 5 times. And then after on the fifth time, you can show me all five, and then I'll say, okay, maybe I believe you. So consistency and association and mechanism is part of this precision that we want to have. Accuracy is where molecular nicknames must be correct. So don't use nicknames, don't use popular names. If they call something a jumping gene, no, it's not a jumping gene. If it's a cancer switch gene in the popular literature, no, it's an oncogene. Don't use non-technical terms. Okay. And there's a difference. I'm sorry, I should explain this. Precision is getting the same thing multiple times. Okay. Accuracy is getting something correct. So you can be completely inaccurate, but very precise. So you can consistently get the same wrong answer. That means you're precise, but not accurate. If you get the correct answer once, but only once, you're accurate, but imprecise. So, having said that, molecular nicknames for accuracy must be correct, and treatments must be accurate. Okay, when you give the drug, you can't just say, well, the blood pressure went up. Who cares? I mean, what does that say? That's completely inaccurate, right? You have to tie it to a pathway. The renin aldosterone system, for example, or an osmotic regulation gene. Correlation does not always equal causation, and this is probably the biggest problem that science faces is that, for example, um, if something happens and another thing happens at the same time, people tend to link those two things. Okay. And that's what we do as children. That's how we learn about the world. But it doesn't always happen that way. And we'll talk about examples of that later. And then for accuracy, we want to use animal disease models because they have high reproducibility. We can create transgenic mice that have human genes that can accurately model a human disease condition. I can use it, then I can send it to Oniwa Sensei, and Oniwa Sensei can use it, and Oniwa Sensei can send it to someone in Britain, and they can use it, and we get similar results. Okay, and
Yeah.
correct results. This is very, very important. Okay,
Mm.
so some examples of the way that a clinician would communicate or the way a clinician would think about something. Let's go to a small journal. Some of you may have heard of it. It's called the New England Journal of Medicine. It has an impact factor of like 70. Okay. And these are all MDs. Some of them are MD PhDs, but notice they don't have any pure PhDs. They have an MB PhD. He should have caught this. We read this. Okay, just this sentence, the highlighted sentence is the incidence of conjunctivitis was higher among patients receiving dupilumab than among those receiving placebo. The cause of conjunctivitis in patients with atopic dermatitis is not yet fully understood. Is that a good sentence? Yeah, if you're a medical doctor, oh, of course, that's a good sentence. So the incidence was much higher, so we have to watch out for that. If you're like me and you have a PhD, whoa, wait, what? What, dupilumab causes conjunctivitis? Why? I don't want conjunctivitis. I already have atopic dermatitis. I don't want other itises. One itis at a time, please. Okay? So, okay, keep reading. Patients with atopic dermatitis, particularly moderate to severe disease, are at increased risk for depression. Wait, what? Is that because I have atopic dermatitis and it makes me sad? Or is there a direct biochemical link? If you read a clinical paper, they don't explain these things. As a scientist, we must know. So, the traditional clinical way to approach this issue of side effects or of associated comorbidities. Why is conjunctivitis higher in atopic dermatitis or AD patients? Well, we'll give steroids locally because that's anti inflammatory, and then we'll wait. If the inflammation goes down, we're good to go. If it doesn't go down, give more steroids or try another anti inflammatory. Depression. Give an antidepressant. Wait. Do you want to kill yourself? No. Okay, good. Problem solved. Because remember, it's effect based, it's outcome based. They don't care how it works, as long as it works. Well, a traditional scientist would say, well, this is completely intellectually unsatisfying. I will take one single protein from the inflammatory pathway, I will isolate it, and I will see if it interacts with anything else. This single interaction will be published in a journal, and I will go home happy. Problem's still not solved. You've only solved one step in the pathway. Depression's the same thing. Okay, well, if the brain's not working, let's get some human brain cells. If you're a neuroscientist, the only two experiments that they ever do are patch clamping or confocal microscopy. Um, and let's do that. And okay, well, we got a cell, we patch clamped it. Now let's put on like 17 different neurotransmitters. We learn nothing. Okay, we published a single step. If we do this, this goes up or down or whatever. So how does that help me if I have atopic dermatitis with conjunctivitis and depression? It doesn't help me. So there is a university in Ochanomizu, and if you were Nintendo, you went into the entertainment industry and became a billionaire. But if you studied hard, you became Juntendo and you became a medical university, right? They're not related. That's just a joke. But these scientists, who are translational scientists, biomedical scientists, found that omega 3 fatty acids suppress allergic conjunctivitis symptoms. And they found, and this is a low resolution from the website, but basically, dupilumab blocks IL 13 and IL 4. just like omega-3 blocks IL-13 and IL-4. Okay, omega-3 are natural anti-inflammatories. So you think, wait, if omega-3 has a similar mode of action to dupilumab, wait a minute, hold on, blocks mast cell activity. So dupilumab should actually lessen conjunctivitis. So this doesn't make any sense. But maybe omega-3, because it's also anti-inflammatory, may ameliorate the conjunctivitis. So something to keep in mind. Prior knowledge on depression from the same methodology would say, okay, here's a paper, Frontiers in Psychology, Influence of Stress and Depression on the Immune System. So chemotaxis of lymphocytes and neutrophils are lower in women with depression. So the immune system is actually depressed. There's chronic low-grade inflammation, and dupilumab may not affect those pathways. Okay, so now we start to see that there are links that are not being explained by single-step interactions on the science side, or the incidence is higher on the clinical side. We see omega-3 fatty acids may affect conjunctivitis. Omega-3 fatty acids may help with depression because it affects inflammation in the immune system, this chronic low-grade inflammation. Huh. Okay, we've got a bunch of prior knowledge now. How do we make this happen? Well, if we take the same two questions and we do them in the translational way, we generate a disease model. Okay, we take mice with atopic dermatitis. We can treat with dupilumab. We can treat with omega-3 fatty acids. We can treat with both at the same time. We can check the expression of genes in the inflammatory pathway and generate a disease pathogenesis model. This happens, then this happens, then that happens. Here is the sequence of molecular interactions and protein modifications that result in this disease. Once you have a battle map, you can start attacking key points with therapies or traditional medicine or tons of fish oil. Depression, same thing. We generate an animal disease model. How do you measure depression in mice? Well, actually, you can because of their activity. You can measure the tail activity, you can measure their social activity and other things. So you can create a depression scale for your mice and then treat them. Treat them with Prozac. Okay, treat them with Prozac and omega-3 fatty acids. See what happens. Check the expression of their neurochemistry, the genes that generate neurotransmitters. Okay, you can check all of these things and generate a pathogenesis model. So just as a hypothetical, so the glial cells, which is basically the brain macrophages, they're activated in atopic dermatitis. They attack and they reduce the level of some transmitter and you get depression. Once you start figuring things out translationally, you start getting foundational key points in the mechanism to develop countermeasures, to develop new drugs with, okay? So we wrap all of this into a translational report where we take the disease model information and interactions. This is scientifically precise. Remember molecular precision and accuracy? Exact proteins, DNA and RNA sequences, specific carbohydrates. We may also have oligos, little short nucleic acid strands. Maybe the flora and the gut affect atopic dermatitis patients. We would put that in too. Whatever induction dosages would be in there. And then a statistical analysis on the effect of the intervention. So if we had 100 mice, then how many were helped by the treatment, how many had no change, that kind of thing. We would then clinically translate that from mice to people. Okay, here's the genes in the mice that we found. Here are the analogous or similar genes conserved in humans. This is the speculation part of the paper. Okay, How do we translate what we found here into the clinical research area? Number three would be the specificity of the chemical intervention. Okay, when we give omega-3 fatty acids, this is what happens after the fatty acid is digested. It has this intermediate. This intermediate interacts with this product on this specific receptor. Okay. How is the molecular regulation changed by the intervention? We would very likely have a diagram. Scientists like diagrams. Figure 7, the last figure, should always be some kind of diagram because that's what I will go to first. If you publish a paper with a complex mechanism and don't include a diagram, I will email you and ask you for one, okay? Because I need that. Then we will suggest future studies, also the basis for clinical trials. What human doses or what human interventions may be relevant? How do you get this thing started is basically what a translational report will do. So we've taken the basic science, we've translated it into enough data and enough correct language so that a doctor, a medical doctor, can say, well, okay, well, we have a drug that affects that pathway in that way. Maybe I can start a clinical trial. But here's some of the side effects that I need to watch out for. Okay. So you're decreasing inflammation to the point where you get gastrointestinal bleeding. Okay, we'll watch for that. So a translational report has scientific and clinically relevant information in it. Okay, so that's the molecular precision and accuracy. Are there any questions about this particular thing to this point? This is a lot of data. I'm talking pretty fast. So if you have any questions, please feel free. Everyone's so polite. Okay, I'll keep going. Now, as scientists, what did I say the hardest thing in the world was? The hardest thing in the world is finding a job. I mean, sorry, the hardest thing in the world is thinking. Okay. I don't know why scientists drink so much. Okay. You shouldn't drink so much because this is all we have. Don't damage the only thing that protects your career, okay? Find another way to relax at night. So I'm going to introduce a concept called the critical thinking chain, and this is something that I've created based on my 20 years in science, and I'll be publishing a book on this hopefully in the next year. And the critical thinking chain is sort of a methodology to have a link between what you want to do and where you are now. So it consists of two basic things, and one is the topic anchor, the second is the question chain. So the topic anchor itself is fairly simple. If you think of it as the picture, it's a chain and an anchor. The anchor is the broad topic. Is it molecular biology? Is it physics? Is it sociology? And this particular concept is not restricted to translational medicine, but it's applicable to almost every field of science. So that's why I'm including it in here. You would need in translational science to use this concept. Okay. But it also includes the subtopic. Is it virology? Is it astrophysics? Is it mass media studies? It doesn't really matter what it is as long as you know what the field is. So one of the problems is when we get multi-front or multifaceted problems such as global pandemics or global warming or artificial intelligence. These are things that are 7 or 8 fields all smushed together into one big problem. Well, you can't do all of the fields at one time. You have to define a single field. Okay, COVID pandemic, public health, public health, public health. That's all we're focusing on. We can't do public health and molecular virology and vaccine development, all these other industrial things. You can't do them at the same time because it spreads out your effort. You need a focused effort here. Just like an anchor, okay? It's heavy. It drops in one location. Yes, ma'am, there's a question.
Yeah, I want to ask about this point. So, if we need to focus only on a specific topic, so at some point for complicated analysis or so on, we need multidisciplinary. So maybe yeah, the main focus will be public health, but at the same time we need like molecular virology or something like that. So I have no idea if this will make the researcher to be like to be confused or cannot help him to focus on a specific topic. But at the same time, he needs this. He needs this type of multidisciplinary and interdisciplinary field to solve his question. So
Sure. And that's an excellent point because the demands of our modern world are basically you multitask normally. Okay. You need to do 10 things at once just in your daily life. Now, if you're going to do something important, you need to do 7,000 things at the same time. Now, how well do you multitask? How well can you drive a car, text on your phone, drink a soda, and talk to your friend? You won't do any of those things very well. So I can say multidisciplinaryism is very good, but there's a proper point to introduce it. Sometimes we get too much multidisciplinary thought at the beginning, and then everything just kind of wanders off non-specifically. So sometimes you want to have an anchor. You want to have a single point. Once you've established the point correctly and you can rely on that data as a foundation, then you can bring in another field. You bring, okay, public health. We understand the way that this virus is transmitted. We understand the R value. We understand the dynamics of it, the infectivity of it. We understand everything about it in this one specific point. Now we're going to develop a vaccine. Now you have a very solid foundation to develop from. So multidisciplinary measures are excellent, but they must be introduced at the correct time.
I see.
Yeah. And so I think we might confuse especially new scientists because new scientists think that they have to be really good at everything, and that's just impossible. Whereas I know scientists who are only good at one thing and they're fully funded. Go figure. Okay. But the important thing is the topic anchor can be just about anything. Now, the thing is, if you want to be multidisciplinary and you just have to do it, well, you can do two topic anchors. Here's the molecular biology anchor, and here is the, let's say, public health anchor. Establish both of them firmly, and then build both of them, either alternating or both at the same time. That way, when they merge, there's still what's called a custody chain. Let me explain the chain, and this will become a lot more clear. So when I talk about a question chain, we're going to talk about what it is, when to use it, how to use it, and who cares about it at all. But the question chain is basically something that connects a surface idea of thought to the very deep topic anchor. It's a chain of what's called intellectual custody. This is the most important word that I can teach you today. And if you don't remember anything about me other than my hair loss, please remember the word intellectual custody because this is very important. If you don't have a mechanistic, logical, and replicable chain of custody, other people cannot follow it. Other people cannot help you. You can't help you. So once the chain is established, other people can follow it so that you can put multiple people on the same job. And that's where the multidisciplinary part comes in. If I establish a topic anchor, sorry, that's very well constructed, then I can have a chain that other people can follow. So the virologist starts first. He creates the chain. Then the public health guy comes in and can follow the intellectual idea to the point, okay, here's where I come in. Then he creates the chain. Okay, now we need to have the manufacturing engineer, how to produce the vaccine quickly. He follows the chain up and says, okay, this is my spot and I'll take it this way. So reproducibility, remember the find part is always has to be reproducible. Um, To be perfectly honest, being right is stupid in science. Right doesn't do anything for us. And I hate to say this because I like to be right and I like to succeed, but answers don't accomplish anything. Only questions lead to progress. Because once we found something that works, we keep doing it. Gasoline works. Penicillin works. Wait, what happens when it doesn't work? Well, then we start creating alternative energy. Then we start creating alternative antibiotics. Humans don't do anything as long as we keep winning. Teams that consistently win never change because there's no need to. You only change when you lose. So that's why a question chain is more important than an answer chain. So I call it the question chain because this is how things go forward. The synthesis of the ideal question is the key to all science. That's what science is based on, hypothesis. Create a question and then test it. Probably learned this in basic science, so that's why I developed the question chain. The question chain is therefore a chain of questions related to forming hypotheses. I'll explain everything. So wait, the question chain is a hypothesis? Okay, these are non-scientists dressed up as scientists posing in a picture. This is a stock photo. These people are obviously not scientists. They're too happy. If they were real scientists, they'd be tired. They'd have dark circles under their eyes and probably a flask of whiskey in one of these pockets, right? Okay. The question chain helps to develop the hypothesis. You do the chain before the hypothesis by ensuring that logic is there. Because a hypothesis requires previous data, previous knowledge. If you just generate a random hypothesis, then you waste your time because it will probably fail. Okay? Humans did this thousands of years ago. Thunder in the sky, everyone is scared. Oh, there's the light in the sky, it's scary. Where does it come from? Well, obviously, there's a god and he's got a hammer. And when he hits his hammer on a rock, it creates the lightning into thunder. Well, that's a random hypothesis. Was it created with a question chain? No, it wasn't. So can you test it? No, you can't. So we learned nothing for 1,000 years, okay? The question chain and topic anchor are basically a hypothesis factory, and I'll show you how that works in an example. But what I want to talk about is layers. And when you think about an anchor and a chain, you think about the ocean. There are layers of the ocean. It's very deep. Okay, it's filled with delicious things to eat and things that think you're delicious. So how do we navigate this wild habitat? Well, all issues and ideas are multi-layered. Nothing is ever super simple. All the super simple stuff has been figured out already. Most of the problems that we face are very complex. As was said by the student who asked the very good question, everything is multidisciplinary by nature. So working down toward the bottom is what we want to go to. We want to get to the source of something. We want to reach the end of the anchor, but it's very dangerous because it's easy to get lost or distracted. It's easy to say, we created a vaccine, it's done, we're safe, we won. And then 5 years later or 10 years later to say, oh, it didn't work at all. Like, what do we do now? And if you don't have a question chain to go back, to backtrack and start over, then it's just random. You have to start randomly, which is no good. Okay. So the question chain will keep you on the path to the good hypothesis. Now, what are the layers? I've defined them in 7 layers because my favorite burrito in America is a 7-layer burrito, but there's also the idea of lucky seven. So I thought maybe it would stick in people's mind. So there's 7 layers: the surface, minor issues, intermediate issues, major issues, the Great Barrier, the bottom, and then what's called the essence. And then for each layer, I have come up with a non scientific, entirely subjective utility rating of 1 to 10, with 1 being the least useful and 10 being the most useful of each layer. So from layer 1, your possible discoveries are 0. which is even less useful than anything else. And as you go up, or as you go down in layers, I should say, and you find out details, and you start finding out context, and you start finding out limits of understanding, and you start getting into the theories and laws of physics and nature, then you start getting some utility, right? You figure out a law and you can use it to predict the future. So 55 years ago, America put somebody on the moon. Do you know why we could put people on the moon? Because the laws of physics allowed us to predict exactly where the moon was going to be. That's unlimited predictive power. That's the goal of every scientist, to find that layer of understanding. So I'll go through the layers very quickly. Layer one is the surface. This is what everyone can see and think. This is what the popular opinion is. This is what someone would say on the street if you ask them a question. Is the vaccine good? Is global warming bad? You know, these kinds of things, like political opinions, are often layer one. It doesn't mean that it's correct. It's just what people think. Okay. Nothing ever comes from this. It's worthless, completely worthless. If someone tells you, I saw on the news that this is bad, you could just ignore them. Okay. Because it doesn't represent what's below it. You can look at the surface of the ocean and it looks perfectly calm. And then underneath the ocean surface, there's chaos. Or, and this is so cool, if you've ever seen video of like a hurricane on the ocean, and then you go like 100 meters below the surface and it's perfectly calm. You would never know there was a typhoon on the surface of the water. So these two things, they don't reflect each other, so we just ignore them. Most of us as scientists will start from layer two, which are the small fish, the zako, the minor issues. These are small things. They're easy to find. They could be something as simple as, what does MRI stand for? Okay. It could be getting supplies or asking the easy question. Global warming, what is global warming? What does that even mean? Define that. Sometimes it's about finding the right people. Oh, before I start, I need to ask the postdoc how to actually do a Western blot, and then I can do a Western blot. Sometimes it's that simple. And if you're dealing specifically in science with a pathway, for example, protein synthesis, it's the single step in the pathway. So you can see where the traditional scientific method that I showed you in the molecular precision section, where it's to do a single step interaction and then publish it. That's just a minor thing. So you'd have to get lots of those together to be useful. The next layer, the bigger fish, these are yellowfin tuna, which are delicious, deals mostly with the management of minor issues as a group. So taking all of these basic science papers and putting them in order to say, okay, this goes to this, then this goes to that, then that goes to that. Trying to link things together in a group would be an intermediate issue. Another common thing to ask yourself at this step is, wait, how many different experiments do I need? Hold on. Let me hold on. Let's see. Okay. I need 7 experiments to get one figure. Okay. The 7 experiments are layer 2 issues. Putting them together into a coherent figure would be the intermediate issue. Okay. It can also, that's why I say it can deal with project management or entire pathways. So, for example, an inflammatory pathway would be an intermediate level. Major issues, this is a whale shark or a jimbei deals with multiple intermediate issues. So you've got inflammation, plus you've got, let's say, steroid pathways. So inflammation and anti-inflammation pathways interacting with each other. That's level 4. Okay, that's maybe 25 papers all put together into a review. It's that level. Understanding things from a big perspective. It can also be the coordination of several projects. For example, sending people to the moon required rocket propulsion chemistry, so that's basic chemistry, solution chemistry, plus computer science to create the guidance module to get the thing into the moon, which is physics and mathematics. But it can also biologically deal with several pathways. For example, protein transcription, which is itself an intermediate issue composed of simpler issues, the minor issues, and then translation. So, two intermediate level pathways coming together. How do they interact? What's in between them? How do they regulate each other? Okay. And then this bumps us into what I call the Great Barrier. And this is the Great Barrier Reef in Australia, which is basically the layer that represents the technological or theoretical limit that we have today. It cannot be broken by conventional methods. It requires innovation. You can't just do Western blots and find a cure for cancer. It doesn't work that way. There's some theoretical barrier that or technological barrier we need to pass. It often becomes the functional bottom. This is as far as we go until innovation can catch up. Now, just because we can't get past it doesn't mean we can't do nice things. We still don't understand how to make a workable, safe, and reliable common cold vaccine. Okay, the coronavirus vaccine that everybody got, you could probably try to use that for the common cold, but it wouldn't work. They've tried for 30 years or 40 years to make a cold vaccine, and it never works. We just don't have the technological expertise to break through the barrier. But that doesn't mean we can't get side benefits. Hey, we can't get a common cold vaccine, but we can have an mRNA vaccine for COVID, or we can have a better hepatitis vaccine or other things. So the space program was 55 years ago, but the technology that it spawned has been used in all aspects of life. Okay. Now, if you can get through the Great Barrier, then you reach the bottom. This is where your anchor is. Okay. This is the core issue, the idea or the answer that holds true for all cases. This is the universal answer for that problem. It's like a law, like thermodynamics. Thermodynamics is layer 6. If you give me a defined system and defined energy, I could take these equations of thermodynamics and 72.74 years from now, I can tell you how much heat will be in that system, how much entropy will be in that system, and it will be accurate. So you can predict the future basically, right? All the above layers are supported by this layer. Do you know that protein translation is actually physics? It's not biology. Because the interaction of proteins is based on chemical affinity, which is based on subatomic particle affinity, the interactions of which are defined by physics. So we have an expression that biology is applied chemistry, chemistry is applied physics, physics is applied mathematics, right? So it goes down the custody chain. So the mathematics of it is the bottom layer, and you can go up from there. Sometimes you can't understand it. We may find something, for example, at the Large Hadron Collider, the Big Particle Accelerator, or the KEK, or the Super Kamiokande, the particle colliders we have in Japan. There might be particles that are being generated that we can't detect. We don't have the understanding to comprehend these things yet. So sometimes you know things are there, but you don't know exactly where. We know when we smash these two particles together, it creates all this stuff. We know it's in there, but we don't know how to find it or we don't know how to explain it. Okay. Now, most of the time we stop at the bottom, but I want to talk about one step further, which is the essence layer. Now, the essence layer is the total reality, the total physics, the total relationships, the total integration and theory of something. This is the water that all of the layers are composed of. If you're in physics, that Higgs boson or that super magic subatomic particle that will explain everything, that's the essence. Once you understand this, you're going to win a Nobel Prize. So the guy who finds that special particle will win a Nobel Prize, hands down. But you'll also understand all six top layers. You'll be able to predict the future. You'll be able to develop perfect things. Okay. However, this cannot be found without innovation. This is why innovation is so important to science. Because if we don't completely understand something at this level, we do things that don't work. Like we start cloning. Everybody wants to clone things. We want to clone animals. We want to clone plants. We want to clone people. But if we don't understand the essence of mankind, of humanity, not just the biological chemistry, not just the physics of the elements within us, the silicon and the carbon and the hydrogen, but the sociology, the psychology, the essence of the soul of humans. We start cloning, you get this. Okay, this is a tank that fell into a deep ocean or something, and the water pressure just smashed it flat. So humans usually fail because they skip directly to layer 7 without understanding the 5 top layers, okay? They get crushed. They don't understand why. They just said, "Okay, uh let's clone humans." And then it doesn't work and they go, "Oh, okay, well that didn't work. I guess I don't know what to do next." You don't know what to do next because you never established the custody chain. You just randomly did something because you thought it was cool. Repeated failures can endanger the entire species. If you want a good example of this, Jurassic Park, the movie. Just because we can do something doesn't mean we should do something. Other things are to remember are that because essence is large, because it's the entirety, it's all layers 1 through 6, the pressure is intense. If you mess up, you get this. It's not a small failure, it's catastrophic. If you engineer a climate solution that affects the whole planet and you're wrong, you ruined everything. If we start a nuclear war and we're wrong, the whole planet is dead. Okay? If you create a medical treatment like a drug and you're wrong, people die. Okay? So, having said that, it has been roughly 50 minutes. So, do you guys want to take a 5-minute break or do you want to continue on? Oniwa sensei, what do you think?
Yeah, whichever is fine, actually.
Okay, what would you prefer, a break or keep going?
I think you can keep going.
Okay, I'll
Then,
keep going.
yeah,
Okay,
why not?
sounds okay. Sounds good. But if you have to,
But if you need a rest, of course you can have.
no, I still have some coffee left, so we're good to go.
So better to go to the toilet.
Oh
Take the
no, no,
coffee.
I'm good to go. I'm good to go.
Okay.
Yeah.
Okay.
So okay, so let's move on to the types of questions that you would ask based on the layer or on the level. So on the surface, the first question you ask is why does everybody think this? The answer is always because that's what they've been told to think. If you're not a molecular immunologist, you don't have an educated opinion on vaccines. You think what you're told to think. If you're not a professional golfer, then you don't have educated opinions on golf. You think what you're told to think. And that's okay because that's how humans kind of get along in the world. We have to do it that way because not everybody can be an expert at everything. So we take something simple, our brain can say, okay, this equals this, just file it away and you focus on other things. Okay. But if you are that person who thinks, okay, global warming is my issue, vaccine development is my issue, this is my career, I got to go deeper. What questions do you ask? The questions that will get you into the minor and intermediate layers are the who, the what, the where, the why, the when, and how. This is traditional. This is like a newspaper article. Whereas when you start getting into the deeper layers up to the barrier, it's mostly how and is. How does this work? And is this really correct? the worst question you can ever ask a scientist. You can go to a Nobel Prize winning scientist's uh, lecture and you can ask one question and make him cry. And the question is, how do you know that you're right? Because layers 6 and 7 are basically, what do I need to know that I know? So, for example, that magical particle that they're trying to find at Keck or the Large Hadron Collider, do they even know what they're looking for? And if they see something, how do they know what it is? If you can't measure it, how can you see it? And then after you find it, it's, oh, what can I predict with this? So will the world, like Americans are fat, and I'm fat too. And as a joke, I always like to say America's going to get so fat that it's going to unbalance the world and it's going to spin incorrectly and just go off into space. Wait a minute, is that possible? Well, if you understand physics, you can probably calculate that. One of the things that we can calculate, for example, are the large earthquakes. For example, the earthquake that just hit Japan, or the big Fukushima earthquake, or the one that hit South America a few years ago. They actually affect the Earth's rotation. There's so much energy released that you can calculate the Earth's rotation was slowed by 0.000004 seconds, something like that. But you can calculate it. It can be predicted. Okay, so let's use an example that will make everybody angry because using an easy example doesn't explain anything. Remember, problems cause progress. So let's talk about global warming. Now, for the purpose of this exercise, whatever I think about global warming is irrelevant. We're scientists. We don't think about what do I think is correct or not. It's what is true or not. And that's why we have to have a custody chain. If I'm tackling global warming as a climate scientist, okay, this is my thing. I'm going to fight global warming. Well, what do I need to know? What terms? Who do I ask? Is there a climate scientist that can explain things to me in an easier way? What single things are critical to this process? When did this happen? Or is it actually going to happen? How do we know it's going to happen? Okay, where will this happen? And at this point, you're only getting answers, and you can find all of these answers on popular websites, no problem. Are any of them correct? Who knows? But now you start getting into the level 2. These are the minor issues, the single steps in the pathway. So if carbon dioxide is so bad, how does it cause warming? What's the mechanism? Okay. What is the pathway of solar fusion? So if the sun energy is what CO2 is trapping, how is that energy from the sun created? Well, if CO2 is in the atmosphere and there's a bunch of clouds, like you can see, I picked this image specifically because it uses clouds to show CO2. CO2 is an invisible gas. But if CO2 goes up in the atmosphere where the clouds are, then do they interact? Because you can dissolve CO2 in water, it creates carbonic acid. And carbonic acid is actually how your body regulates its blood pH. Okay? So wait, CO2 and water interact. Does that even work? If it did, and that's what actually happens, where does it happen? Does it happen in the upper atmosphere, in the lower atmosphere? Does it happen outside my back door while I'm sleeping? Okay. And then if we go to these intermediate issues, now we start getting into interactions of large systems. If one country, so let's say for example, Japan is an advanced economy and it has a higher CO2 output from manufacturing. New Zealand, which is a smaller country with less manufacturing, has a lower CO2 output. So does that mean that Japan gets warmer than New Zealand? Because it's outputting more CO2, so the concentration is higher here. It should get warmer here, right? I don't know. We have to find that out first. Do clouds contribute? If we have a lot of cloud cover and a lot of the sun's energy is getting in, does that help or hurt? Do clouds block heat? We don't know. I don't know. I'd have to figure that out. But Also, what systems can we manipulate? So let's say we find out that clouds are helpful. They block heat. Can we create clouds? Can we generate like a lot of steam and make clouds in a warm area like a desert so that it cools off? Who knows? These are things we need to ask. But when we start getting into level 4, remember, these are the major issues. These are the molecular interactions. So on a planet level, the big level, what happens to the dark side of the planet when the light side is warming? There's no sun energy on the dark side, so the dark side cools down. We know that at night it's colder, but if there's global warming and CO2 in the air, will the nighttime temperature be warmer than the daytime temperature? What energy system is responsible for that? How is global weather affected by increases of a single degree? If we're going to remodel the entire world economy to avoid a temperature increase of 1 degree or 2 degrees, will that make a difference? The answer to that, if you ask the question, is shut up and give me your money. There is no real answer because we cannot yet predict that far ahead. Okay. Another question may be, okay, well, if carbon dioxide, let's say I've discovered carbon dioxide is a big greenhouse gas and it's bad. Well, how do we capture it? And there are people working on that right now. Let's capture carbon from the air and put it underground. Let's lock it into the ocean. Okay. Let's put it in big storage tanks as liquid carbon dioxide, liquid CO2. Or if you're a computer scientist and a climate scientist, then, well, I have a global simulation that takes all of these complex issues and has a model. Well, how do I check the accuracy of that? What's the way to do that? How do I evaluate my complex system? And this leads us into basically what is the barrier, the current barrier that humanity faces. How do we know that a 1 degree increase will be catastrophic? We really don't, because global temperature data from 50,000 years ago is not nearly as accurate as global temperature information from modern instruments yesterday. We can measure temperature to the 17th decimal point. If we estimate based on, for example, ice cores or fossil records or tree rings from 70, 100,000 million years ago, it doesn't have 17 decimals of precision. So if we take precise data and imprecise data and we multiply them together, do we create precision? Do we create accuracy? We don't know. We really don't. But is what we currently know enough to act on? And how can we be sure we can recover if we're wrong? If we re engineer the entire world's economy to reduce carbon dioxide, is it going to work? Is some volcano going to erupt under the ocean next year and put out 100 times more CO2 than humans have in our entire existence? We don't know. There's things that we cannot yet predict. Remember, we're only at level 5. We're not at level 6. We can't predict the future very easily. And is CO2 a sufficient target that we can precisely control? There are other greenhouse gases. There's methane, there's polyfluoral alkalized substances and other things that are much better at trapping heat energy than CO2. So why did we choose CO2? Who knows? Now, I sound like a skeptic, but I'm not a skeptic. Okay, I do believe that global warming is a problem, but I can't say that I'm educated unless I can get down to level 5 and I know everything up to this level of understanding. Now I can have an educated push to basically level 6, and this is cool. This looks like Japan's most expensive rice cooker. They have those $1,000 rice cookers from Mitsubishi. This does not cook rice. It is a quantum computer. It is a very elementary quantum computer. The problem with global warming is we don't actually know level 6. We're not there yet. It probably deals with particle interactions that are so complex We need quantum computing to model it accurately. So in this case, level 5 is a technological barrier. Innovation can push us through. Maybe we can get enough computer power to model this. Because if we could, we might see that interventions that are proposed aren't going to work because we can predict the future. Now, in our lifetime, we may not cross this barrier for global warming, but we may cross it for other topics. Okay. Now, level 7, we know it has something to do with physics. Okay. Physics explains everything. We know that. But specifically, we don't know. It's probably thermodynamics, but we cannot answer the question, how do we know that what we know is what we know? How do we know that what we know is correct? The question, what do I need to know I know, has not yet been answered truthfully. Now, maybe the discovery of that magic particle explains thermodynamics. And now we say, okay, all we have to do is measure the particles in the atmosphere. Now we can use quantum computing to predict the spread, and that affects global warming. That's a hypothesis. You can test that. Okay. So those are the 7 levels and an example of the thinking at every level. Now, when do we use this? Well, everything is a hierarchy. Everything is ranked in science. And we instinctively understand this as humans because basically even something as chaotic as war has ranks. You know, here's the guy that's giving the orders, here are the people that are following them. So everything is ranked. So always establish the topic anchor first before the question chain. Get your specific area. Get the chain developed before making the hypotheses because it's not useful after a failure unless recovery is possible. If you fail and you can't go back and start here instead of all the way at the beginning, then you failed yourself. So, for example, if we have a climate solution that fails, we can't walk back 20 years and reset the atmosphere. So we need to have a chain so that we can kind of go back and say, okay, everything was good up to this point. From this point, it was bad. Let's walk it back to that point if we can, and then try to repair the damage. And that's what a chain allows you to do. Now, the easiest part of this entire lecture is how to use the chain. And although it'll be difficult to read because it's my handwriting and I don't write very well, uh, I just write things out on a sheet of paper. Take a sheet of paper, lines or no lines. Use your favorite pen, the Pokemon pen that you got for your birthday, and write down what you know, the topic anchor, the surface layer. What do we know? Well, we know this, we know this. The global temperature's up, disasters are up. Okay, layer 2, minor issues. Who, what, where, why, when, how. Remember the questions I gave you. Well, who? Who is most likely affected? Everyone. Okay. What does GCM mean? Okay, well, that's global climate model. That's a definition. Okay, where's the heat concentrated? From the National Oceanographic and Air. It's basically NOAA is the environmental arm of the US government. Globally, the temperatures are 0.06 Celsius more than average. Okay. Why does CO2 trap heat? Here's a reference. You can look this up. When will the Earth heat up? Here's a reference. This is a predictive model. How is CO2 released? Well, here's how much is released, 36.8 gigatons. And this website tells you the breakdown. There's agriculture, there's cars, there's transport like boats and ships. Okay, there's agriculture burning, that kind of thing. Now, from each one of these, I can generate a hypothesis. Who is most likely to be affected? Everyone. So, once I take all of this into account, the heat is concentrated in the ocean because water absorbs lots of heat. Maybe people near the ocean are affected because of ocean rise or because of the heat generated by the ocean. Maybe CO2 in clouds trap heat, so the Mojave Desert, which has no clouds most of the time, is proportionately more affected. Maybe CO2 And why it traps heat? Well, these are polyfluoral alkylinated substances like Teflon, like non-stick coatings. They trap heat 10 to 100 times more than CO2 because of infrared energy absorption. It's these double carbon bonds. The double carbon bonds actually hold heat energy. Okay. Well, I'll test CO2 versus this PFAS and see which holds more heat energy. Okay. So by just answering these questions, so I do this. If it's got a circle next to it, I can probably make a hypothesis out of it. Okay. If it's just an X, that's just a fact. That's just to educate myself. Ah, okay. GCM is global climate model. Okay, that's just a piece of data to help me later on. But anything with a circle can generate a hypothesis. So by just generating the second layer of the chain, I've got 4 fresh hypotheses. And on the third layer of the chain, I may generate another 4 hypotheses. And as I go down the chain, I'm generating more and more and more hypotheses to test. Now, if any of those hypotheses don't work, I just go back up 1 layer. Okay, wait a minute. Maybe one of these hypotheses is not working. If something looks good, then I can develop from that. Okay, that's why it's important to have a chain. Now, why use it at all? This is a lot of work. You have to sit down with a sheet of paper and you have to do things. This is not cool. There's PlayStation 5 and TikTok and Nomi Hodai. Like, why should I do this thing instead of those things that I like to do? Well, the reason is because it allows you to follow the chain at a later date. There have been many, many times in my science career where I did something that I didn't think was important. And it got put away, I did other things, and then 7 months later, I had to go back to the first thing. And then I took out my notebook and said, What? What does this mean? Why did I even think this? And I had to start all over. I wasted 2 or 3 weeks preparing myself, reading the papers, trying to figure out the logic of what I was doing, generating a decent hypothesis. Okay. If you have all of this written down, you just keep it. 7 months later, you look at it, oh, yeah, 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 layer 1, 2, 3. I'm at layer 3, and here's the hypothesis. Also, you can bring other people in. You can get the new postdoc to help you. The postdoc says, what are you working on? Let me show you the sheet. Here are the layers, here's the facts and other things at each layer, and here's the process that I followed. Now I need to generate a new hypothesis. Now he knows everything about it. It also keeps things organized. It keeps you from going from like, here's a single step interaction in layer 2, now we're on layer 5. Let's create this complex system, which is what humans tend to do because we want everything now, 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 now. Okay, we know this 1 plus 1 equals 2. Now do differential calculus. Yeah, it's like those art tutorials on YouTube. You know, you start with a circle, you put 2 dots for eyes, and then 5 seconds later, it's the Mona Lisa. It's like, wait, how do you go from there to there? It just skips. Okay. The other thing is it creates hypotheses that are relevant and focused. It's focused on your topic. It's focused on the appropriate layer of information. Okay. So what I would like for you to do is if you want to use this principle, you're welcome to do so. But think of the anchor, do the question chain, and then formulate your hypotheses. They'll be more targeted. Trust me. I use this myself. I developed this in graduate school. And it took me a while on every new project to get started. There'd be 2 weeks where I was just doing this. And everybody would kind of look at me and say, oh, he's just sitting there. He's doing nothing. And then I would lay out all the hypotheses, all of the plans and procedures. And my professor would look at the proposal and he would say, I like this. I see exactly where you're going with this. I can also predict things that need to be done if things don't work. If this Western blot doesn't come out correctly, all we know is that the regulation is probably pre-translational. So here's that branch of the chain. Okay, I've already gotten that hypothesis ready. Okay, last but probably least, or not least, is the manuscript dissemination. Okay, this is the tell part. And I'm going to show you why it shouldn't be the most important, but it is. If you are a professor or a postdoc or somebody who needs to publish to get promoted, you already know where I'm going with this. Okay. Manuscript dissemination. The goal of science is to discover. Communication is the co-goal. It is of equal importance. Okay. We do this with standardized manuscripts. If you do not publish it, it does not exist. Okay. It doesn't matter what you discover, you do not get credit unless it's published. It doesn't matter how nice a guy you are, or how incredibly handsome you are, or how many classes you teach, or whether the gifts you give to your colleagues at Christmas are expensive or cheap. It only matters what you publish. The university will look at you and say, "You didn't publish, leave." The grant agency will say, "We gave you 25 million US dollars. You published nothing. You wasted our money." Right? So these standardized manuscripts have become a very important part of translational medicine or translational research. And writing papers is probably the most important part of science, but not medicine. So again, there's that fundamental disconnect between the clinical and the scientific side. In the science side, you must, and let me just explain it this way. Manuscript dissemination is done through peer-reviewed journals. I don't care if it's on Facebook. I don't care if it's in some kind of popular science journal, IFL, I something love science.com or whatever. It's useless. It has to be in a peer-reviewed journal. Now, conferences and seminars are fun, but they're completely useless. Nobody presents data that's not already going to be published. You'll never see something at a conference that's super important that's not going to be in paper format a month later. Nobody presents data that hasn't been published yet because someone will steal it. Conferences are a way for us to network with each other, to find collaborators, and to get incredibly drunk. So, for example, the American microbiology conferences always have unlimited beer. And you go there to drink beer and talk to your friends, and those discussions create collaborations. Now, those collaborations, the fruit of the collaboration is always going to be a paper published in a peer-reviewed journal. So even if they got rid of every scientific conference on the face of the earth, scientific innovation would continue forward because the goal is to publish. We would send each other emails or have Zoom meetings. Okay. If it's not published, it doesn't exist. It doesn't matter if you presented it at a conference. It doesn't matter. It has to be published. Now, sometimes a scientist can present something that will be published by the conference organizers. That would count. Okay. Now, on the other hand, medicine, well, their manuscripts are published through peer-reviewed journals too, but seminars, continuing education, workshops, hands-on training, these kinds of things are equally important. Because remember, medicine is an effect-based outcome. If I don't publish any papers, and most medical doctors in America aren't expected to publish, they're expected to heal patients. Well, I never published a paper, but I treated 700 patients with COVID and all of them lived. Good job. You get a promotion. Okay. Doesn't even have to be published, doesn't have to be official, doesn't have to be anything. It just has to work. So, for example, in America, doctors are allowed to prescribe drugs off label. That means I can take a blood pressure drug, not for my blood pressure, but for some other issue. That's a very frequent thing for America. And I might find out, I might say, my patients who have depression, they take this drug and their diabetes goes away. So I just prescribe it. Okay, you've got diabetes, but not depression. Take this antidepressive drug. Your diabetes will go away. Hey, it works. So I'll call up my buddy and say, hey, man, give this depression drug. It cures diabetes. Does it have to be published? No, it just has to work. Now, how does translational how do we work? We work basically like science. Okay, in translational medicine, you have to publish it for it to count. But we also publish something called a white paper. A white paper is a recommendation paper that we can send to the government or we can send to lawmaking groups. So, for example, there's a COVID pandemic. The doctors are doing these things, they work. Okay, the doctors are saying, hey, if I put peanut butter all over the forehead of my COVID patients, they all get better. And then the scientists are saying, it's the protein in the peanuts is interacting with the spike protein. Okay, we take this from both sides, we put it together, and we make an explanatory document for policymakers. Now the United States government says, okay, we're going to have a vaccine program and we're going to have a peanut butter program. Okay. So we have to be good with all forms of communication as medical scientists. Okay. We're not doctors, we're scientists, but we interface with doctors and we interface with people who are related to medicine. So the manuscript itself in a translational document is going to look a lot like this. There's going to be some clinical data, whatever. There's going to be some science data. And then there's going to be some translation from one to the other. There's always a transition. It's a smooth transition. So how do we structure the papers? These papers are structured as a standard format. Now, a clinical paper has a completely different structure because it's not a science paper, but a translational or a medical science style paper will be structured as a normal science paper, usually. There'll be an introduction, a methods, results, and a discussion. It'll be slightly different, but this is the usual format. And for the purpose of this presentation, I'll use this as just a way to talk about the different sections, okay? So the introduction, it's a good place to start, right? Introductions rely solely on what's called prior art. In our case, we wouldn't use basic science only. We would use basic science and clinical science. We take a clinically relevant finding and then we draw scientific value from it. Okay, this particular clinical trial found that when they took the blood pressure medication, a significant reduction in blood pressure was seen. It's item one. Smith and colleagues found that this drug interacts with this molecule that reduces the level of renin in the blood, therefore lowering blood pressure. We've put those two things together. We have a clinical result and a molecular effect. We've associated those two things. That's the molecular precision and accuracy. Remember? We can draw from science papers and extract translational value from it. If Tanaka and et al. Discovered that this drug kills this bacteria by slowing its protein synthesis. Well, this other bacteria that causes disease that's related to the original one might be affected too. It has the same cell wall structure or protein synthesis structure. Okay. So this allows us to set up what's called a hybrid hypothesis that has both clinical and scientific value at the same time. I'll give you an example. Let me give you an example. It'll be clearer. This is a paper on NRF2, which is my favorite gene. It's my favorite protein. Um, I did my dissertation on CYLD and NRF2. NRF2 is the antioxidant response gene. Okay. So if we look at this, we see that the yellow are the clinical. Remember the diagram before? The yellow are the clinical parts. Aging is associated to reduction in NRF2 activity. Data show that upregulation of NRF2 can render neurons resistant. That's a very clinical statement. It has no reasoning behind it. It's just this is what happens. Okay. Take this, this happens. This is the scientific, the modulation of genes, specific genes. Okay, here's the specific regulatory sequence. Here is the modulation factor, keep one. All right. Again, a clinical, many dietary inventions modulate NRF2. So this is energy and high energy consumption, energy regulation and high energy consumption are the most studied strategies and both modulate NRF2. Okay, well how? What? How? Well, here we go. Energy regulation increases NRF2 activity, okay? And once you get restriction of activity, it triggers this pathway. That's the translation. You see where I'm coming from? You have clinical statements that have nothing to back them up. It's just this is what we observed in patients. Then you have a scientific thing that says this is what NRF2 does. Now you've linked two things together. Dietary restriction causes the NRF2 ARE, antioxidant response element pathway, to increase. That's what causes the clinical effects that are seen. Okay? So that leads to the hybrid hypothesis. A sample clinical hypothesis would be something like if we do A, we get condition B. Condition B, patient gets better. My patient is upset. I slap my patient in the face and say, get a hold of yourself. 5 minutes later, the patient is okay. Therefore, let's do a clinical trial. We'll take a bunch of depressed people, we'll slap them in the face, and then after 5 minutes, we'll see who's happy and who's not. It's a perfectly valid clinical hypothesis. A science hypothesis would be Y happens because of X, W, R, and Q. Depression is a loss of serotonin. Serotonin production is affected by these four genes. These four genes are modulated by this intake of da 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 da. Okay. A hybrid hypothesis would combine these two things. Y happens because of X, W, R, and Q. We know that. Therefore, if we do A, then A affects X, W, R, and Q to cause Y to happen. All of this results in condition B, and the disease gets better. So you see what we take a clinical hypothesis that has no molecular machinery, and then we take a science hypothesis that is only molecular machinery, and we link the two things together to a disease condition. Now, if you're not good with like letters A, B, Y, X, Q, W, if you weren't good at math like me, this is a real world example. Okay, these guys are, and you can actually email Dr. Battist. Hey, Dr. Battist, I saw a screenshot of your paper. Can you explain it to me? Sure. A NRF2 inhibitor selectively sensitizes KEAP1 mutant tumor cells to cisplatin and gefitinib, these are chemotherapy agents, by restoring NRF2 inhibitory function of KEAP1 mutants. Wow. NRF2 inhibitor. That's science. That's molecular biology. I give this drug, I can inject it into a mouse. It inhibits NRF2. It sits on the transcription area, okay? Or it increases the constitutive inhibitor of NRF2, either way. Well, the cisplatin gefitinib response is clinical. I give this drug, do tumor cells die? Do I care how they die? No, just that they do. But now we have a molecular mechanism. If we activate KEAP1 to suppress NRF2, that reduces the antioxidant level in the cell. Therefore, the chemotherapy, which acts by reactive oxygen species to kill the cell, will be more effective. We've taken a science and a clinical finding and we have translated it into a hybrid hypothesis that we can now test in a mouse disease model. Does everyone, I hope, see how we're trying to blend these two things together? That's the communication part. So a scientist looks at this paper and says, man, that's some mighty good molecular biology. And a clinician looks at the paper and says, wait, if I give a NRF2 inhibitor to my patients who are on chemotherapy, they could get better results. Let's do a clinical trial. So we make both people happy. Yay. Go biomedical science. Pay us more. Okay. For the methods, for this reason, you need to use molecular precision in both parts and be very precise in the details because remember, the doctors will want to know approximate blood volume. No, they want to know precise blood volumes. 70 milliliters of blood was drawn from each mouse. Okay, well, if 70 milliliters was drawn from each mouse, mice don't have much blood to begin with. Proportionately, how much blood are we going to take from the human? Oh, okay, well, if it's 10 times, so 700 mils, that's a lot of blood. Yeah. So doctors will be thinking along those lines, whereas the molecular precision will be for the scientists. And then actually the level of detail in the methods, believe it or not, is set by each journal. Let's go over a quick example. KLF4 is a zinc finger protein. It's a Yamanaka factor for making stem cells. So the materials and methods here, you can look. Let's take a look at just this one. The ovarian cancer SCOV3 and OVCAR3 cell lines are obtained from the American type culture collection, cultured in DMEM, and then here's the different stuff that they put in it. Cool. However, this particular journal, okay, here we go, like total RNA, 3 to 5 micrometer curls cut from paraffin. Okay, that's fine. How much total RNA? Oh, who knows? Whereas in this one, it's okay. We've got the specific culture conditions, the specific gas conditions. We've got the specific lines. We've got empty vector adenovirus, add GFP or add KLF4. We've got 100 nanomolars of non-targeting silencing RNA. Okay. What are you using? Lipofectamine 2000, and this is the exact reagent. So, although we may want to be ideally very precise and accurate in our methods so that we can make both the doctors and the scientists happy, sometimes it's up to the journal. Okay. So just to let you know as a warning that the methods may rely on the journal, but this is a translational. KLF4 defines efficacy of erlotinib in triple negative breast cancer. So triple negative breast cancers are hard to treat because you can't attack them with anything. So now they're checking this and they're checking a molecular key in that pathway. For the results, we're almost done. Use precision in detailing them, especially in interaction experiments, so like phosphorylation. Specify phosphorylation. Don't just say post-translational modification. There's methylation, there's sumoylation, there's phosphorylation. There's all kinds of ations that happen post-translationally. Be precise. But give the interpretations of the data as single conclusions so that people can take those away however they want. Let me show you this. This is from our hospital, from the Institute of Medicine, and I can just say Dr. Chiba is a MD PhD. He's a hematologist. He's one of the smartest scientists I've ever met, and is one of the best writers ever. And I'll show you why. Because he takes these figures and he boils them down into a single sentence. This is myeloid leukemia. Okay, so if we look back here, so leukemia propagation. This fatty acid gene regulates chemotaxis, which is chemical movement, via this pathway following this chemokine stimulation. Chemokine is something that causes chemical movement and is involved in mouse AML. So if you are a general scientist, you would say, haha, PI3K and LOVL6 have some kind of direct interaction. You'll run with that. If you're a clinician, you'll say, wait, my patients have leukemia. Maybe I can test this gene. We can create a profile. If you have high levels of this in your tumor, then that means your tumor is advanced. We can use this as a biomarker. And if you're a translational scientist, you think, oh, I have to kill a bunch of mice with leukemia. I will never have a holiday again. Okay. So basically, this has something in it for everybody. Now, if we take this example here, let's just look at this particular part. CXCR4 signaling depends on this activation of downstream cascades. So this is very, very, very complex scientific, right? So we look here. Everything was summarized. The pan-AKT inhibitor this did not alter this, suggesting this. Oh. So if these cells are cancer cells, and this gene does not really affect these cancer cells, then as a clinician, as a doctor, checking for this is not useful. That's good to know. As a basic scientist, wait, this pan inhibitor, how does this thing work? How does it bind? Like, what's the physics of the binding of this MK whatever to these cells? Okay, he's got something to be happy. As a translational scientist, I go, okay, well, inhibiting AKT doesn't really help with leukemia. So by just writing a simple conclusion, each type of researcher, clinical, scientific, or translational, gets something out of it. All right, last but not least is the discussion. This is the most important part because it places everything in context. Remember at the molecular precision section, I told you that the translational report is for everybody. It lists everything in scientific detail, but with clinical relevance. Clinical relevance. It's highly comparative. This is incredible. Highly comparative is the most important part. Because all the speculation is based on clinical and science studies. We're tying the two things together. So future directions are both clinical and scientific. And most include study limitations, actually. I'll show you some examples of this, and this is where we analyze. So if you are a medical scientist and you discover something or you are testing something, we have tested 750 patients with leukemia. Here are the genetic markers that we found. Here's 5 of them. Now, here are the groups of chemotherapy that they're on. And here's the level of those 5 genes in each one of those chemotherapy groups. Well, that's very useful for a clinical doctor. That's also very useful for a basic scientist. But as a translational scientist, we go further. We analyze it. We say, hey, these older people benefit from this particular chemotherapy because it downregulates these oncogenes a lot better. We give an analysis of a clinical prediction. Okay. But this section, to be honest, operates in the reverse of the introduction. The introduction went clinical, translational, science. The discussion usually goes science, translation, clinical. Let me show you, like, this is reverse. Let me show you this in an actual paper. Here's Nerf 2 again. If you ever want to get on my good side, talk about Nerf 2. This is my mentor, actually. I got my PhD with, Taixing Cui. Now, he created this beautiful diagram, probably in Word. It doesn't look very good, but it shows you the different interacting factors and the different mechanisms. Okay, so when he discusses it, this is the science part. DH404 induced NERF2 nuclear accumulation involves other regulators, such as nuclear dissociation. It might activate kinases to phosphorylate and stabilize. Remember, specificity and regulation. That's a science thing. Other cysteine residues, such as cysteine 275 of KEAP1, might contribute to this. Cool. Now we have the translation. It is noteworthy that this mechanism, which he's just explained the molecular precision of, is a unique NERF2 activator. Unlike this, we observe that ultipraz is a clinically used medicine. It's a prescription drug. Now we get into the clinical translation. They're similar, but unlike that, it's an established NERV2 activator. It induced increases in superoxide and peroxynitrite. Now we have a clinical explanation. Although it is unknown whether the strong side effects observed in ultipraz trials in cancer chemoprevention is caused by this, da 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 da. So we've given scientific precision. We've given a transition into from the bench into clinically relevant medicine. And what does that medicine mean clinically? Okay. And then in this other one, we've got another. If we characterize this, then it'll facilitate novel therapeutic strategies for the treatment of cardiac diseases. Okay. In the dupilumab one, remember this one? This was the one we looked at before. In contrast, a clinical paper, dupilumab was good. Dupilumab was great. Dupilumab was cool. That's it. We're done. So you can see that the contrast in a clinical paper versus what, like, for example, a translational or a medical scientist would use. So to wrap everything up so we can get some questions. Remember
Yeah,
that,
thank you. Yes,
yeah, of
yeah.
course, yeah, we're
I'm a
done.
bit worried when
Nope,
you are closing
I have a watch.
your talk, but I think that yeah, now it's good. Now 5 minutes we have a Q&A session.
Exactly. So this is the
Yeah.
summary. So thank you for listening. I know your legs are probably asleep, but if you want to ask questions, please feel free to do so.
So Farag-san, please.
Uh, Firstly, thank you for your presentation.
Sure.
Secondly, um, actually, when okay, so my master's degree was in pharmacogenomics, so I was testing specific what will be the effect of a specific SNPs on different proteins and enzymes that interact with multiple drugs by using bioinformatics and computational approach. So when it comes to translate this, I've reached in my thesis and research, and I wanted to translate it to real life on the Egyptian population, I faced new limitations. And there were like new limitations start to appear that I don't have the chance to face them before, and those limitations actually hinder me to translate what I did in the basic or like the basic research to transfer this into the real statement. So how to overcome those limitations? So I see that okay, we will go like through different layers. We will do this in the wet lab and the basic research. But when it comes to translation, again we faced new limitations that we cannot like even expect them. So how to overcome those limitations? How to be flexible enough to fix those limitations? So
Well, that's a very good observation. It's a good question. And the answer is I've basically taught you how to do your end of the bargain. So how to fulfill your side of the commitment. When society asks you for something, this is how you give 100%. Now, once you've given 100% and you found the solution, your government has failed you and your leaders have failed you because you've given them something that they don't want to do because they put a lot of obstacles in your way. So the way to overcome that is to replace your government. If you can't do that, then you have to go through political systems. I don't know anything about politics. I'm politically neutral, but I can say that based on the surface level of understanding, things get easier or harder. So politicians never understand anything past layer one. If you find something that doesn't agree with their layer one interpretation, you get nowhere. So sometimes when we find the truth, it's impossible to translate it and everybody suffers. So all you can hope for is that maybe 20 years later, maybe a scientist gets elected or your scientist becomes president and reads what you wrote because you have an intellectual custody chain. Scientific president will be able to read that and say, this is logical. We need to do this.
mm,
So all you can do is what you can do. And don't worry about what other people can do. It's not a good answer, but it's the only one we have.
yeah, I see. You're right. Thank you.
Okay. Sure. Are there any other questions?
No.
Somebody's got a question. I mean, it could be like, "Hey, Brian, how'd you lose all your hair?" Or, you
Hello,
know,
Oh,
"What's your favorite food?"
can I
Yes,
speak?
yes, of
oh,
course, yes.
Okay. Thank you very much for your wonderful and interesting. I feel very lucky to hear such a lecture in the first year of my PhD, and made me rethink the way I think. And I think these valuable contents need time to digest.
Sure.
Um, I have worked in the field of child development for 8 years, and last year I made the decision to continue to do the research. So I applied for the PhD course, and of course, I also very deeply felt the gap between the clinical thinking and the scientific thought. And that is also a great challenge for me now. I think, I mean, how to use scientific thinking to think about problems encountered in my practice. And thank you. I have learned a lot from your lecture. My question is that. mm, which level of the layers do you think we need to reach as a PhD student?
As a PhD student, the level you need to reach is a single paper to graduate. Nobody, please do not save the world until after you graduate and after you get tenure, because science does not reward failure. If you start trying to do too much at one time, then you become you could lose focus. So for example, if you find a single element of the pathway for in your field, for example, maybe you find that the increase of the internet
Mhm.
is making single mothers rely more on the internet as a surrogate childcare provider rather than a professional childcare provider. What's the psychological impact of that? Okay, well, there's 7 layers to that, but you only need to get to about layer 2 or 3. If you find a single step where, okay, educational programs are beneficial, entertainment programs are not beneficial,
Mm.
publish that, graduate, get your next job, and then start going for level 3, 4, 5, or whatever. I want to encourage PhD students to graduate at all costs. Do not shoot for the moon because
Okay.
you're not going to make it. I mean, just do something that's within your reach. So just maybe level 2 is okay if you get a paper out of it. If it's a saturated field like molecular biology, you may have to do level 3. The simple stuff's already been figured out. Now you have to figure out mechanistic interactions between two complex systems. But I think in your field, because there's really no connect between the clinical and the science, as you've said, the simple things will work. Go level 2, graduate.
Okay, thank you very much. I got your point.
Sure.
Thank you.
Mm.
Um, Before everybody leaves, I just want to say that this is very, very helpful for anyone who is interested in having a scientific career. I think it's, Brian, as usual, last year your talk was very clear
Oh,
too.
thank you.
This year is so clear and very kind of precise and with a peculiar sense of humor.
Thanks.
So I really appreciate, and maybe when after this course, I could get a permission from you and from Professor Oniwa that I can share with some of the graduate students of NCKU,
Sure, I'll send
so they
these.
can.
I'll send these slides. That this is the final version, and I'll send these to
Mhm,
Oniwa Sensei, and you can freely share them with your graduate students because we want to increase the global level of science. This may be a good way to do it.
So
And I also want
also,
to add it.
yeah,
Just
also,
one last point is
Hmm.
it would be interesting to put you together with a philosopher of science because they're interested in the thinking process and epistemology. So I think it will be very interesting. Sorry, I interrupted you, Professor Oniwa.
oh, no, no, fine. Actually, I'm also recording this series. So,
Mhm.
and we can share our movie, yeah, how to say, lectures
Great,
with your,
great.
yeah, colleagues or the students. But please do not distribute freely. Okay. Later, I'm
Sure,
going
sure,
to,
sure.
yeah, I'm going to share the link of the YouTube.
Okay.
Okay.
Great. Thank you.
Sounds good. So thank you everybody for giving me your time and your attention. If you have any questions, you can contact me. Professor Oniwa has my address, and
Yeah.
you can feel free to email me.
Yeah.
I can't help you with a job offer, but I can help you with general advice.
Mhm.
Mhm.
Okay, so Brian, thank you very much. Yeah,
Thank
and
you.
next is Morio Sensei, and I think we just have the 5 minutes break. It's too short, I think. After the
Yeah.
very, very nice lecture from Brian. So we shall start from the 10:15 in
Sure.
NCKU, and 11:15 in Tsukuba, Japan.
Okay.
Okay,
Okay.
Morio
Sure.
Sensei. Okay, oh, you.
I see
Okay, so
Morio
10 minutes.
Sensei is already here.
Yeah. Yeah, anyway, 10 minutes break.
Yeah.
Okay.